Tonight, imagine something you can't touch, can't see, yet it's always wrapped around you. It never stops, never turns back, never waits. It was here long before you were born, and it will linger long after everything grows quiet. We call it time. But what is time? Why does it flow in only one direction? And does it truly exist, or is it simply the way our minds make sense of the universe? So tonight, as your eyes grow heavy and your breath softens, drift with me into the gentlest mysteries of time. No rush, no worry, just a quiet sense of wonder, and sleep waiting patiently at the edge. If these peaceful moments bring you comfort as you loosen your grip on a long day, stay with us. Let this channel be the place you return to each night, where science and sleep melt into one. Subscribe if your heart feels like it, and let the universe's soft secrets keep you company in the dark. Let's start with a small experiment. Right now, as you're lying here, try to feel time itself. Don't look at a clock. Don't count the seconds. Just sense it. Can you? Time has no smell, no sound, no shape. You can't touch it the way you touch the blanket over you. You can't see it the way you see the moonlight slipping through your window. And yet you know it's there. You can feel it drifting past, like an invisible river carrying you from one moment to the next. Time is one of the deepest mysteries of existence. We live inside it. We measure it. We try to save it, kill it, buy more of it. But no one truly knows what time is. Philosophers have argued about it for thousands of years. Scientists have studied it through microscopes and telescopes. And still, hidden in plain sight, remains the simple, profound question, what is time, really? Maybe the best place to begin is with how we experience it. Every morning you wake up carrying the memories of yesterday. You know breakfast comes before lunch. You know winter follows autumn. There's an order to things, a sequence stretching from past to present to future. We call this the flow of time, and it feels absolute. It feels like the most fundamental rule of reality. But here's the strange part, the deeper we dig into science, the more we realize that this feeling, the sense of time flowing, might be nothing more than an illusion. Something our brains create to make sense of the world. The physical reality of time is far more complicated and far stranger than what we feel when we close our eyes and try to fall asleep. To understand how we got here, we need to go back to the first people who tried to make sense of time. Thousands of years ago, across ancient Egypt, Babylon, China, and India, humans looked up at the sky and watched the planets wander, the sun trace its path through the stars, the moon swell and shrink. They saw seasons change, people age, children grow. From these observations they realized something was happening, a process, a shift, a movement from what had been to what would be. So they began measuring it. First with the sun, day and night. Then the moon, months. Then the stars, years. They built sundials, water clocks, hourglasses. Each tool was a way to mark the passing of this invisible thing, something everyone felt but no one could grasp. Pause for a moment. Think about all the generations who lay beneath the night sky the same way you are now, wondering about the nature of time. The same questions. The same wonder. The same mystery stretching across centuries, untouched by any clock we've ever built. For the ancient Greek philosophers, time became a battlefield of ideas. Heraclitus argued that everything flows, nothing stays still. You can't step into the same river twice, he said, because the water is always moving, always new. Time, to him, was the most fundamental reality, eternal change. But Parmenides disagreed. He claimed that change itself is an illusion. Only the eternal, the unchanging, is real. Time, he said, is something we imagine, not a true feature of the world. Then came Aristotle, trying to chart a middle path. He defined time as the measure of motion in terms of before and after. In other words, time exists because things change. Without motion, without difference, there would be no time. But this raises a strange question. if nothing changed, if the universe froze perfectly in a single instant, would time still exist? Or would it vanish, like a sound disappearing when there's no ear left to hear it? These aren't just philosophical puzzles. They go straight to the heart of what time might be. And as modern science began probing time with more powerful tools, these ancient questions became more important than ever. Now let's turn to a different kind of question, one you've probably never stopped to consider: how does your brain create time? Because the time you experience, the feeling of seconds, minutes, hours, isn't the same as the time described by physics. Your time is personal. It stretches and contracts. It slows down when you're afraid and races when you're happy. It shifts with age, mood, and whatever you're doing in the moment. Think about a dangerous instant, a fall, a near accident. In those seconds, time seems to slow to a crawl. You remember every detail with strange clarity. Scientists don't think the brain actually slows time down. Instead, it records more memories, more details, so when you look back, the moment feels longer than it really was. Your brain was working overtime, snapping more mental photographs, and later, when you replay the scene, it feels like the film is running in slow motion. And then there are the days when time just vanishes. You sit down to work in the morning, and suddenly it's late afternoon. You pick up a book, and hours slip by like minutes. Psychologists call this the flow state, when you're so absorbed that your sense of time dissolves. Your internal clock seems to switch off, and you drift through a kind of endless present. Kids experience time differently from adults. For a 5-year-old, a year is a fifth of their entire life, a massive chunk. For someone who's 60, a year is just 1/60th. That's why childhood summers feel endless, while the adult years seem to accelerate, running faster and faster as we age. Our brains keep what's known as an internal clock, a neural system that tracks durations. But it's nowhere near as precise as a wristwatch. It's influenced by temperature, emotion, attention, even medication. Caffeine makes your internal clock tick faster, so time feels slower. Some drugs do the opposite. When you're bored, the clock drags every second out. When you're engaged, it flies. And then there's memory. The way we remember time is nothing like the way we live it. A 2-week vacation full of new experiences can feel long in hindsight, while 2 weeks of doing the same routine every day can shrink into a blur. Our brains record novelty, not repetition. So a life filled with change feels longer when we look back, even though it passed at the same steady pace as any other. All of this points to a strange truth: the time you experience isn't the objective time out there. It's a construction of your mind, built from memory, attention, and the neural rhythms of your brain. In a sense, each of us lives in a slightly different universe of time, a universe that doesn't quite match the one belonging to the person sitting next to us. But what does physics say? Is there a real time, a time that exists independently of how we feel? For centuries, people thought so. Isaac Newton, the great physicist of the 17th century, believed in what he called absolute time. He imagined time as a giant cosmic river, flowing at a constant rate, untouched by anything. Whether you were standing still or running, whether you were on Earth or drifting in deep space, Newton's time flowed exactly the same for everyone, everywhere, forever. It was a beautiful idea. Clear, comforting, and completely wrong. It turns out time isn't a cosmic river. It doesn't flow at a fixed speed. It can slow down. It can speed up. It can bend and twist. And the discovery that shattered the foundation of science came from a young man working in a patent office in Bern, Switzerland, in the early 1900s. His name was Albert Einstein. And the story of what he uncovered, how time truly behaves, is one of the most beautiful and bewildering tales in the history of science. But before we get there, let's pause for a moment. Let yourself drift a little deeper into rest. Let your breathing soften. Because what comes next isn't something to rush through. It's something to sit with, to let settle, like snowfall on a quiet night. We began with a question: what is time? And what we've learned so far is this: it isn't what it seems. It isn't fixed. It isn't absolute. It isn't the same for everyone. And the most wondrous part, the part we're about to explore, is that time and space aren't two separate things. They're woven together into a cosmic fabric Einstein called spacetime. And that fabric can stretch. There's an experiment you can try right now, even if you're lying there in the dark. Think of a memory, one that still feels vivid, maybe from your childhood. Maybe it's a warm summer morning. Maybe it's the face of someone you love. Maybe it's a moment of pure joy, or a deep, aching sadness. Now ask yourself, where is that moment? It's not here, in this room. It's not on the bed beside you. It's gone. It belongs to the past. And yet in your mind, it's alive. You can see it, feel it, almost touch it. So where does that memory actually exist? In your brain, yes, as patterns of firing neurons. But the moment itself, the moment that really happened years ago, where is it now? This is one of the deepest questions about time. Does the past still exist? Or has it vanished, dissolved into nothing, leaving behind only traces in our minds? And what about the future? Tomorrow hasn't happened yet. But it will. So is it out there somewhere, waiting? Or does it not exist at all, just a possibility, a ghost of what might come? Most of us imagine time as a road. The past behind us, the future ahead, and we stand at one point, the present, moving from one to the other. The past is gone. The future isn't here yet. Only, now, is real. But some physicists disagree. They argue that the past, present, and future all exist at the same time. Every moment, every second of history and every second yet to come, is real right now, all at once, inside what they call the block universe. Picture a book. Each page is a moment in time. As you read, you move from one page to the next. But all the pages exist simultaneously. Page 1 doesn't disappear when you reach page 2. The final page is already there, even if you haven't reached it yet. In this view, time doesn't flow. It simply is. Everything that has happened and everything that will happen lives inside a single eternal structure, and our consciousness just travels through it, experiencing it one moment at a time. Strange, right? Almost impossible to believe. But that's what Einstein's math points toward. And a few astonishing experiments back parts of it up. Of course, not all scientists agree. Some argue that only the present is real, and the future isn't fixed, it's open, shaped by choices and randomness as we go. In this view, the universe isn't a solid block but an unfolding process, a story being written in real time. So who's right? Does time flow, or is that an illusion? Does the future already exist, or is it being woven together right now? Oddly enough, the answer might be both. It depends on how you look at it. That's what makes time so slippery. It's not like other scientific questions where you can run an experiment and get a clean answer. Time sits on the border between physics and philosophy, between the objective and the subjective, between mathematics and consciousness. It's the bridge between the physical world and the world we experience within. Maybe that's why it fascinates us so much. Because to understand time is to understand the universe, and ourselves. It's science and mystery wrapped together. Let this sink in for a moment. Let it drift across your mind like a cloud sliding through the sky. You're lying here, in this moment. But what is this moment? Is it the meeting point of past and future? Is it all there ever was? Or maybe, just maybe, it's both, and neither, all at once. There are no easy answers. But these questions open a door. And behind that door lies one of the most beautiful discoveries in science, a discovery that forever changed how we understand reality. Think about this, for over 200 years, from Newton's era up to the early 1900s, science believed in a clockwork universe. Time ticked evenly. Space stretched out unchanging. And everything moved through them like gears in a giant machine, predictable and obedient to simple mathematical laws. Then Einstein arrived. And with a handful of simple yet profound ideas, he dismantled the cosmic clock. He showed that time isn't a gear. It flows. Space isn't rigid. It stretches. And together, they form a single entity, space-time, capable of bending, twisting, even tearing under the right conditions. It was a revolution. And it all began with a question a 16-year-old boy asked himself while walking home from school: what would happen if you could chase a beam of light? That question, simple, almost childlike, led to one of the deepest theories ever conceived. We're going to follow that story, stepping gently through discoveries that even now, more than a century later, still astonish scientists. We'll explore how time slows down when you move faster. How it nearly stops near a black hole. And how, if you could travel fast enough, you could leap into the future while the people you love grow old without you. But don't worry. We'll take it slowly. We'll move with curiosity, not haste. Because these ideas, these beautiful, strange ideas, deserve to be savored like a long, slow feast, not swallowed like fast food. Take a deep breath. Let your shoulders sink into the pillow. And as you drift toward the edge between waking and sleep, know this: the story of time, our strange, beautiful, unbelievable story, is only beginning. And as thoughts of time start floating and dissolving in your mind, one feeling remains: wonder. Because time, whatever it is the strangest gift we have. Every moment is a tiny miracle. Every breath is a chance to be present, to feel, to be alive. In our next journey, we'll explore what happens when time bends, when it stretches and slows, when reality reveals itself not as a ticking clock but as a symphony. But for now, rest. Let the night wrap around you. And if sleep comes before the story ends, that's perfect. Because time, in all its mystery, will still be here when you wake. Always flowing. Always waiting. Always inviting us to look a little deeper. Imagine a 16-year-old boy walking home through the quiet streets of Aarau, Switzerland. It's a late summer afternoon in 1895, sunlight dripping through the trees and brushing the sidewalk with soft golden streaks. As usual, the boy is lost in thoughts most people would never even consider. He's wondering what would happen if you could run fast enough to catch a beam of light. If you could fly alongside it, look straight at it, what would you see? That boy was Albert Einstein. And that simple question, dreamed up by a curious teenager wandering home on a warm summer day, would eventually overturn 3 centuries of physics and open a completely new way of understanding reality itself. But not right away. It would take 10 years of thinking, struggling, and slowly piecing things together before Einstein could unravel what that question truly meant. And when he did, he found something no one expected: time isn't constant. It's not the same for everyone. It can stretch, shrink, slow down, and in extreme situations, almost stop. Let's start with what people believed before Einstein. For more than 200 years, ever since Isaac Newton, science had been built on a simple assumption: time is absolute. It flows at the same rate, everywhere, always, for everyone. You could be on Earth, on the Moon, or racing through space at terrifying speed, it wouldn't matter. Time would tick the same. A second for you was a second for anyone else. An hour here was an hour there. Simple, clear, absolute. But Einstein realized something was off. Because there was a strange fact about light, one scientists already knew but hadn't understood the full meaning of. Light always moves at the same speed. No matter how fast you're going, no matter whether you're chasing it or running away from it, light always races through space at the exact same speed, about 300,000 kilometers per second. Nothing goes faster. Nothing catches up. And nothing slows it down or speeds it up. It's bizarre when you think about it. If you're standing still and someone shines a flashlight at you, the light reaches you at 300,000 kilometers per second. But if you run toward the flashlight at, say, 10 kilometers per second, you'd expect the light to hit you just a bit faster, right? Like running toward a thrown ball, it reaches you sooner. But no. The light still comes at you at 300,000 kilometers per second, exactly the same. How could that possibly be? How can light have the same speed for everyone, no matter how they move? Einstein realized there was only one way for this to make sense: time and space must change. They have to stretch or shrink to keep the speed of light fixed. If you're moving very fast, time has to slow down for you. Space has to contract. Not by much at everyday speeds, you'll never notice it driving a car or flying in a plane. But as you get closer to the speed of light, the effect becomes dramatic. And the astonishing part is that it's not just theory. It actually happens. We've measured it. We've seen it. We even have to account for it in our everyday technology. Let's pause here for a moment. Let that idea sink in. Time isn't a constant. It isn't the same for everyone. Right now, as you sit quietly, time flows at one rate for you. But for an astronaut aboard the International Space Station, orbiting Earth at about 28,000 kilometers per hour, time is running just a little slower, only a tiny fraction of a second per day, but measurable. It feels almost impossible to imagine. But it's true. In 1971, two physicists named Joseph Haffel and Richard Keating set out to run a simple, almost poetic experiment. They took 4 atomic clocks, the most precise timekeeping devices humans had ever built, capable of measuring time down to billionths of a second. 2 clocks stayed on the ground, tucked safely inside a lab. The other 2 were carried onto commercial airplanes and flown around the world. When the clocks came back together, the scientists compared them. And just as Einstein had predicted more than 50 years earlier, the clocks that traveled aboard the airplanes ticked ever so slightly slower than the ones that stayed behind. Only a few billionths of a second, an amount so tiny it feels impossible. But it was there. Measurable. Real. Time had literally slowed down for the moving clocks. Sit with that for a moment. These clocks weren't malfunctioning. They didn't get it wrong. They experienced less time. If you replaced those clocks with 2 people, one staying on Earth and the other flying away at incredible speeds for many years, the traveler would age more slowly. When they returned, they would be just a little younger than the person who stayed home. This isn't science fiction. This is the universe we actually live in. Time isn't a rigid track we all march along together. It's more like a fabric that stretches and squeezes depending on how fast you move. But motion isn't the only thing that bends time. Gravity can do it too. Einstein discovered this a few years after his first groundbreaking theory. He realized that gravity isn't just a force pulling things downward. It's the bending of space and time itself. Picture a tightly stretched sheet. If you place a heavy ball in the center, the fabric dips, forming a well. Smaller objects rolling nearby fall toward that dip, not because some invisible hand is tugging on them but because space itself is curved. That's gravity. That's how the sun keeps planets in orbit. It's why you're stuck to the Earth. Not because something is yanking you down but because Earth's mass warps the space around it, and you're simply following the curve. And here's the magical part: when space bends, time bends with it. Wherever gravity is stronger, time runs slower. Again, this isn't philosophy. We can measure it. If you take 2 atomic clocks and leave one at ground level while placing the other on a mountain, where gravity is just a bit weaker because you're farther from Earth's center, the mountaintop clock ticks a little faster. Time passes more quickly at higher altitudes. The difference is tiny, far too small to notice in everyday life. But it matters. In fact, the Global Positioning System, the GPS inside your phone, has to account for this. GPS satellites orbiting Earth experience time differently for 2 reasons: they're moving fast, which slows their clocks, and they're farther from Earth's mass, which speeds them up. If engineers didn't correct for these distortions, your GPS would be off by kilometers within hours. So every time you open your map app, you're leaning on the truth that time is not constant. You're navigating using Einstein's equations. Take a breath. Let your brain rest for a moment. These ideas sound impossible, don't they? Time flowing at different speeds. Time slowing down when you move fast. Time stretching and squeezing near massive objects. Everything about this feels wrong to our instincts. But that's the beauty of science. It doesn't care about what feels right. It cares about what is right. And the deepest layers of reality, the actual physics of our universe, are far stranger and more wonderful than anything we could invent. Now let's push this idea to its extreme. Imagine a place where gravity isn't just strong, but overwhelmingly strong. Strong enough that space doesn't form a gentle dip, but collapses into a bottomless well. Strong enough that even light can't escape. A place we call a black hole. Near a black hole, time doesn't just slow a little. It crawls almost to a halt. If you could fly close to the event horizon, the boundary beyond which nothing returns, and hover there safely, watching, each hour you experience could equal many years or even decades for someone far away. You'd watch the universe age around you and fast forward. Stars would be born and die. Galaxies would swirl and drift. And for you, only a few hours would pass. It sounds like science fiction, but it's pure math. This is exactly what Einstein's equations predict. And we've seen evidence of this behavior in the way objects move near black holes. There's a famous movie, you've probably seen it, called Interstellar. In one scene, a team of astronauts lands on a planet orbiting close to a supermassive black hole. They spend only a few hours on the surface. But when they return to their ship, they discover that more than 23 years have passed for the crewmate who stayed in orbit. He's aged 23 years while they've only lived through a few hours. That wasn't Hollywood exaggeration. That was real physics. The director worked with Kip Thorne, one of the world's leading experts on relativity, to make sure the science was accurate. And the numbers check out. Near a black hole that massive and spinning that fast, time dilation can be that extreme. You see, time isn't something absolute or universal. It's personal. Two people can experience completely different amounts of time depending on where they are and how fast they're moving. And both of them are right. Neither is wrong. Time genuinely flows differently for each. This leads to one of the most famous puzzles in physics, the so-called twin paradox. Imagine two twins. One stays on Earth. The other boards a spaceship and travels at nearly the speed of light before coming back home. For the astronaut, the trip might feel like just a few years. But when he returns, he finds his twin has aged by decades. It isn't a real paradox, there's no logical contradiction. It's simply a strange consequence of how time works. And again, it's not just theory. We've seen a similar effect with subatomic particles in accelerators. These unstable particles normally decay in millionths of a second. But when they're pushed to nearly light speed, they last much longer by the lab's clocks, because time for them slows down. We live in a universe where time can stretch and squeeze like rubber. And that tells us something profound about the nature of reality. It means there is no universal now. No single moment that sweeps across the entire cosmos for everyone at once. Your now depends on where you are and how fast you're moving. What feels like the present to you could be the past to someone else, or the future to someone else entirely. It sounds impossible, doesn't it? But think of it this way. Picture two observers drifting through space, billions of kilometers apart. One is moving toward you, the other away. For each of them, the set of events they consider to be happening right now is slightly different. At everyday speeds the difference is tiny, but it's real. And as the speeds increase, that difference grows. In a sense, spacetime is like one enormous block, a four-dimensional loaf in which all events, past, present, and future, coexist. But the way you slice through that block, what you experience as now, depends on your motion. Different observers slice the loaf at different angles, creating different sequences of now. It's like, imagine a loaf of bread. If two people cut it at slightly different angles, each slice captures a slightly different part of the loaf. They're cutting the same bread, but they get different slices. That's what now is in relativity. Let's pause for a moment. Take a slow, deep breath. Let these ideas settle, like gold dust sinking through still water. Time isn't what you think. It isn't a single river we're all drifting along. It's flexible, personal, intertwined with space and motion and gravity in ways we're only beginning to understand. And this strange, beautiful idea began with the simple question of a daydreaming teenager wondering what it would feel like to chase a beam of light. Einstein didn't have an expensive lab. He didn't have supercomputers. He had imagination, a pencil, and paper. He invented thought experiments, hypothetical worlds he could reason through step by step. And from those mental experiments, he built a theory that forever changed our understanding of the universe. But he didn't stop there. After discovering that time could slow down and space could contract, Einstein pushed further. He spent the next 10 years wrestling with an even harder question: how does gravity actually work? And the answer he found was even more beautiful. He realized that gravity isn't a force in the usual sense. It's geometry. It's the shape of spacetime itself. Objects with mass, stars, planets, you, me, bend the fabric of spacetime around them. And other objects move along those curves, not because they're being pulled, but because they're following the natural path through curved spacetime. Earth doesn't orbit the sun because an invisible string tugs on it. Earth is moving along the straightest path it can through the spacetime curved by the sun's mass. From Earth's point of view, it's traveling straight. But because space is curved, that straight line becomes a circle. It's one of the most profound ideas in the history of science. And it was confirmed quickly. In 1919, just a few years after Einstein published his theory, astronomers observed a total solar eclipse. They photographed stars near the sun and discovered their light bent as it passed by. The sun's mass had warped space, and the starlight followed that curve, exactly as Einstein predicted. Overnight, Einstein became a global celebrity. Headlines declared, "Time and space bent." And the world never looked at the universe the same way again. But the story doesn't end there. Because if time can slow down, if space can bend, if the fabric of reality itself can stretch and twist, what else might be possible? Could we twist it enough to travel into the past? Could we bend it enough to make a shortcut across the cosmos? And what happens when spacetime is stretched to its absolute limit, when it tears apart? Those questions lead to mysteries even deeper. Soon, we'll explore one of the biggest of them all: why does time only move in one direction? Why do we remember the past but not the future? And in a universe where time can bend and stretch, is it even possible to reverse it? But for now, rest for a moment. Let your mind drift. These ideas, these strange, dazzling ideas, don't need to be understood perfectly right away. They're like starlight. You don't need to grasp them. Just look, and wonder. There's an experiment you can try right now, inside your mind. Imagine a glass slipping off a table and falling to the floor. You can picture it, right? It drops, hits the ground, and shatters into hundreds of glittering pieces scattered across the tiles. Some fragments are big, others as fine as dust. Each one skitters off in its own direction, slows down, settles, and goes still. Now imagine the reverse. Those shards, all of them, at the same moment, leap up from the floor. They fly toward each other in perfect coordination, snapping back together like a cosmic puzzle, reforming into a flawless glass. Then the glass lifts off the ground and lands gently back on the table, whole and untouched. Can you picture that? Technically, maybe. But you'll never see it happen. Not in a billion years. Not in a billion years. It just doesn't happen. But here's the strange part: the fundamental laws of physics never say it can't happen. If you look at the equations that describe how particles and forces behave, the deepest rules that govern the universe, they don't care about the direction of time. They work the same whether you run them forward or backward. A ball rising through the air follows the same laws as a ball falling. Two particles colliding and flying apart follow the same equations as two particles approaching each other and touching. In theory, everything could run in reverse. So why doesn't it? Why does time move only one way? Why do we remember yesterday but not tomorrow? Why do things age, decay, fall apart, but never spontaneously reassemble? This is one of the deepest mysteries in science. And it has a beautiful name, the arrow of time. Physicists have wrestled with this question for over a century. And the answer they found leads to something strange and elegant called entropy, a measure of disorder, randomness, the amount of chaos in a system. And inside entropy, we find the clues to why time flows the way it does. Let's start with a simple idea. Picture a room. In one corner, there's a box filled with gas, say, air. All the molecules are crammed inside, packed together. Now you lift the lid. What happens? The gas molecules rush out. They spread across the room. They mix, drift, disperse, and eventually fill every corner and every little nook. After a while, the gas is evenly distributed. Some molecules drift near the window, some near the ceiling, some near the floor. Random. Messy. Scattered. Now ask yourself, will those molecules ever naturally gather themselves up and return to the box? No. They never will. Not because they can't. In theory, if every molecule just happened to move in exactly the right direction at exactly the right moment, they could. But the odds of that happening are so tiny they might as well be zero. It would take far longer than the age of the universe, many times over, for it to happen by chance. That's entropy. It's the tendency of things to move toward disorder, randomness, spreading out. A shattered glass has higher entropy than a perfect one. A room full of dispersed gas has higher entropy than a room with all the gas trapped in a box. A hot cup of coffee cooling down gains entropy as its heat spreads into the air. And here's the key, in our universe, entropy always increases. Not because there's a rule forcing it to, but because there are simply far more ways for things to be messy than orderly. Think of a deck of cards. There's only one way for the cards to be in perfect order, ace through king, all suits aligned. But there are countless ways for the deck to be shuffled. So if you randomly scramble the cards, you almost always end up with a messy deck, not a perfect one. That's why time seems to move in only one direction. Not because physics demands it, but because of probability. Because there are far more ways for things to be disordered than ordered, the universe naturally drifts from order to chaos. And we call that direction, the future. The arrow of time is drawn by entropy. Now, think about memory for a moment. Why do you remember the past but not the future? It feels obvious, of course you can't remember something that hasn't happened yet. But pause and look a little deeper. Why not? If the laws of physics don't care which way time points, why do our memories care so much? Once again, the answer comes back to entropy. A memory is a kind of record. It's a pattern in your brain, a set of connections between neurons shaped by your experiences. When something happens to you, your brain stores information by forming those connections. And the act of creating a record, any record, raises entropy. Imagine writing a note. You start with a blank sheet of paper, neat and pristine, low entropy, and you mark it with ink. You've added information, sure, but you've also increased the total entropy of the system. The ink spreads, heat from your hand dissipates, molecules move and mix. To make a record, you have to increase the universe's overall disorder. The same is true for memories. For your brain to record an event, it burns energy, produces heat, and raises entropy. And because entropy only rises toward the future, we can only create records of the past, not the future. That's why you remember your breakfast but not tomorrow's dinner. Not because the future doesn't exist in some mystical sense, but because the thermodynamic arrow of time only lets records form in one direction. This idea is profound. It tells us that our experience of time, this feeling that the past is fixed and the future is wide open, doesn't come from the deep structure of the universe. It comes from entropy. It comes from statistics. It comes from the simple fact that there are many more ways for things to be messy than to be orderly. But here's where it gets even stranger: entropy increases only because the universe started in an incredibly low entropy state. Think about that. If the universe had begun in complete chaos, everything already mixed, already spread out, there would be no arrow of time at all. Everything would just stay chaotic. Nothing would unfold in any meaningful way. But our universe didn't start that way. It began in an extraordinarily low entropy state, all energy and matter packed tightly into a hot, dense point. The Big Bang. And ever since, the universe has expanded, cooled, and drifted toward disorder. That's why time has a direction. That's why the past and future aren't the same. That's why we age, why stars burn, why coffee cools, why memory works the way it does. It all goes back to the universe's initial condition, an unbelievably low, mysterious entropy state at the dawn of time. Take a breath. Let the idea settle. The arrow of time, our sense of flow, our sense of past and future, isn't a fundamental feature of reality. It's a consequence of probability. A consequence of initial conditions. A consequence of how the universe began. But let's go even deeper, because hiding here are questions that get much stranger. If the laws of physics don't care about time's direction, could there be regions of the universe where time runs backward? Physicists have wondered about this. And the answer is, maybe. In theory. If you could create a region where entropy decreases instead of increases, time in that region would appear to run in reverse. Processes would rewind. Effects would precede causes. Memories would point toward the future instead of the past. But there's a big problem: lowering entropy in one place means raising it somewhere else. That's the unbreakable rule of thermodynamics. You can tidy a messy room, but in doing so you burn energy, give off heat, and increase the universe's total entropy. The sum always goes up. So while small pockets of decreasing entropy can exist temporarily, like when a tree grows, building order from chaos, the big picture is always one of rising entropy. The arrow of time points the same way for the entire universe. At least, that's what we think. But some physicists have suggested even stranger possibilities. What if the universe doesn't have just one arrow of time, but many? What if there are parallel universes where time flows in different directions? Or what if, on the largest scales, the universe is time-symmetric, one half expanding forward from the Big Bang, and the other expanding backward, forming a mirror universe where time runs the opposite way? These ideas are speculative. We don't have evidence for them. But they remind us of something important: there is still so much we don't understand about time. There's another way to think about the arrow of time, one that feels a little closer to how we actually experience it. It's the idea of causality. Causes come before effects. You drop a glass, and then it shatters. You never see it shatter first and then let go of it. That order feels absolute, fundamental, unbreakable. But why? Why do causes always come before effects? Once again, the trail leads back to entropy. Causality, this chain of causes and effects, only makes sense in a universe where entropy is rising. As entropy increases, information spreads out. Events leave traces. And those traces let us build a story about what happened, a sequence that runs from past to present. If entropy ran backward, the story would do the same. Effects would seem to come before causes. But to someone living inside that universe, experiencing time in that direction, everything would still feel normal. They'd remember their past and not their future, the only difference being that those words would mean the opposite of what they mean to us. And that leads to a strange philosophical question: does time actually flow? Or is that feeling just part of how a static, unchanging reality seems from our point of view? Some physicists think time doesn't flow at all. They argue that the past, present, and future all coexist, a four-dimensional block of spacetime where every event that ever happened or ever will happen is equally real. The feeling of flow, the sense that now marches from past to future, is an illusion, a side effect of the way our consciousness experiences reality. Imagine a movie. The whole thing already exists on the disc. Every frame is there from beginning to end. But when you watch it, you experience it one frame at a time. The motion, the unfolding story, comes from the way you play it back, not from the movie itself. In this view, the universe is like that movie. All the frames of time exist at once. But our consciousness plays them in sequence, creating the illusion of movement, the illusion of time passing. It's a beautiful idea, but also an unsettling one, isn't it? Because if every moment exists at the same time, then the future is already set. Every choice you'll make, every thought you'll ever have, every experience you'll ever live through, all of it already exists, in some sense. Free will dissolves into a trick of perception. But not all physicists buy that picture. Some argue that the future isn't fixed at all, that it's still being formed, shaped by our choices and by the random quantum events unfolding beneath everything. In this view, only the past and the present are real. The future is a cloud of possibilities, undetermined and open. So who's right? Does time flow, or is it an illusion? Does the future already exist, or are we creating it as we go? The truth is, we don't know. It's one of the deepest questions in science and philosophy, and the debate is far from settled. Maybe both perspectives are right in their own way. Maybe the question itself is flawed, based on assumptions about reality that aren't quite correct. But that's part of the beauty. Time, even after everything we've learned, still keeps its secrets. It still invites us to wonder, to explore, to imagine. So take another moment. Let these ideas drift through your mind like soap bubbles floating in the air. They shimmer. They're delicate. And they catch the light in unexpected ways. The arrow of time is one of nature's most elegant mysteries. It's why we have memories. Why we have history. Why stories make sense, because they have a beginning, a middle, and an end. Because things change. Because time, in all its mystery, seems to move. And maybe, just maybe, that arrow isn't a curse at all but a gift. If time had no direction, if everything happened all at once in no particular order, there would be no growth. No learning. No journey from the unknown to the known. No story worth telling. The arrow of time gives us direction. It gives us meaning. It transforms existence from a static collection of moments into an adventure, a journey through a vast landscape of possibility. And as you lie here, in this moment, on the edge between waking and sleep, you're part of that adventure. You're moving along the arrow. You're experiencing rising entropy. You're forming memories, leaving traces, adding your own story to the great story of the universe. That's the wonder of it. Not because we understand it completely, but because we can wonder about it at all. Because we can lie beneath the stars and ponder the nature of time. Because we can feel its mystery and marvel at it. In the next part of our journey, we'll go back to the beginning. We'll return to the Big Bang, the moment time itself began. We'll explore the first seconds of the universe, when everything we know burst forth from a point smaller than an atom. And we'll ask the ultimate question: what came before the Big Bang? And does that question even make sense? But there's no rush. We have time, whatever it is, however it works. It surrounds us like air, invisible but always present. So breathe. Let your shoulders sink. Let your thoughts drift like leaves floating down a stream. And if sleep comes, let it. Because even in sleep, time continues. The arrow flies. Entropy rises. And the universe keeps dancing its ancient dance, a dance we're part of whether we're awake or dreaming. Imagine being able to step backward through time. Not just a few years or centuries, or even a few millennia, but as far back as time will let you go. Past all of human history, past the birth of Earth, past the formation of the sun, past the generations of stars that came before, past the galaxies drifting slowly in the dark. Back, farther and farther, deeper into the past until you reach a point where you simply can't go any further. Not because there's nothing left to see, but because time itself stops there. About 13.8 billion years ago, everything began. Not in one spot in space, but everywhere at once. The entire universe, everything that ever existed or ever will, was packed into a point unimaginably small, unimaginably hot, unimaginably dense. Then, in a moment beyond comprehension, it expanded, not into pre-existing space, but creating space as it grew. And with space, time itself was born. We call this the Big Bang. But it wasn't an explosion in the ordinary sense, no roaring blast, no fireball tearing through darkness. It was the arrival of reality itself. The moment time switched on. And tonight, as you rest quietly in the dark, we're going back to that moment. We're exploring the first seconds of existence, the moments when everything was set in motion. And we'll ask the question countless people have wondered while staring up at the night sky: how did all of this begin? Let's start with the evidence, because the Big Bang isn't just an idea or a theory. It's the best explanation we have for what we actually observe in the universe. And there are three main clues, three pieces of cosmic evidence left over from that moment of creation. The first clue: the universe is expanding. In the 1920s, an astronomer named Edwin Hubble, the same Hubble the famous space telescope is named after, made a stunning discovery. While observing distant galaxies and measuring the light coming from them, he noticed something strange. The light was shifted toward the red end of the spectrum, an effect called redshift. The reason is simple: those galaxies are moving away from us. Not just a few galaxies. All of them. In every direction, and the farther away they are, the faster they're receding. The universe is expanding, like a balloon inflating with galaxies as tiny marks on its surface drifting apart as it grows. If the universe is expanding now, that means it used to be smaller. And if you rewind far enough, everything must have been compressed into a single point. That was the first hint of the Big Bang, a moment when the universe began expanding from an incredibly dense state. The second clue: the cosmic microwave background. Imagine being able to see the light from the Big Bang, not from stars or galaxies, but from the moment of creation itself. It turns out you can. It's all around you right now, invisible to your eyes but detectable with the right instruments. In the 1960s, two scientists named Arno Penzias and Robert Wilson were testing a sensitive radio antenna. They kept picking up noise, a steady hum coming from every direction in the sky. At first they thought it was a mistake. They even cleaned pigeon droppings off the equipment, thinking that might be the problem. But the noise remained. Eventually they realized they had discovered something extraordinary: the afterglow of the Big Bang. In the universe's first moments, it was too hot for light to travel freely, like a thick, glowing fog. But after about 380,000 years, space cooled enough for light to finally break free. And that light, the radiation from that early moment, is still here, stretched into microwaves by billions of years of cosmic expansion. It's the oldest portrait of the universe we can ever hope to see. A picture not of objects, but of light itself, light from a time when the universe was nothing more than a hot, bright cloud, with no stars, no planets, nothing but energy and possibility. And the third piece of evidence is the ratio of the elements themselves. When scientists look around the universe, they can measure how much hydrogen, how much helium, and how much lithium exists out there. And what they find lines up perfectly with what the Big Bang predicts. In the first few minutes after the universe began, when everything was still unimaginably hot but starting to cool, the first subatomic particles, protons and neutrons, began to latch onto each other, forming the nuclei of the very first elements. Mostly hydrogen, a bit of helium, a trace of lithium. And the calculations for what should form under those conditions match exactly what we observe in the universe today. 3 clues. The universe is expanding. Light from the earliest moments still hangs across space. And the ratio of the elements fits what you'd expect from a hot, dense beginning. Together, they paint a clear picture. The universe had a starting point, and we can still see its fingerprints. But that brings us to a bigger, deeper question: what were those first moments actually like? Try imagining it. Or really, don't, because it's almost impossible. But we can follow the math, follow the laws of physics, and see where they lead. At the very first instant, what physicists call time zero, everything we know was compressed into an impossibly tiny point, something known as a singularity. Temperature, infinite. Density, infinite. Time itself, meaningless. The laws of physics as we know them, shattered. This is where our science hits its limits. We don't have a theory that can describe what happens at the singularity. Einstein's general relativity, our best theory of gravity and spacetime, says the universe began from an infinitely dense point. But it also says that at that point, the theory breaks down. Infinity isn't a number you can plug into an equation. It's a sign that something is missing. But we don't need to understand the absolute first moment to understand what happened right after. And right after means intervals so small they almost have no meaning. At 1/10⁻43 of a second, the universe was hotter than a billion degrees. No atoms, no particles as we know them. Just a molten sea of pure energy and the most fundamental building blocks imaginable, quarks and gluons, the building blocks of the building blocks. Everything was almost uniform, almost perfectly smooth, but not quite. Tiny fluctuations, tiny ripples in the fabric of energy. And those tiny imperfections would eventually seed everything. Stars. Galaxies. You and me. Then, within the first trillionth of a second, something astonishing happened. The universe went through a period of unbelievably rapid expansion called inflation. In a moment smaller than a blink, space itself ballooned outward, doubling again, doubling over and over, dozens of times in a flash. A region smaller than an atom stretched into something larger than a galaxy. Why? Physicists think it had to do with a strange type of energy that filled space in those earliest instants, an energy that produced negative pressure and drove space to expand faster than the speed of light. Then, just as suddenly as it began, inflation ended. The energy transformed into matter and radiation, and the universe kept expanding, but far more slowly. Inflation explains so much. Why the universe looks the same in every direction, because everything came from one tiny region stretched smooth. Why we see small fluctuations in the cosmic background, those are the imprints of quantum ripples blown up to cosmic size. And why the universe is flat, because any curvature would have been ironed out by that rapid expansion. Take a breath. Let your mind rest on that for a moment. In a fraction of a second, the universe grew from smaller than an atom to larger than a galaxy. Everything you see when you look up at the night sky, all the stars, all the galaxies, all the space spanning billions of light years, once fit in the palm of your hand. Smaller. Smaller than a pinhead. Smaller than an atom. As the universe kept expanding, it cooled. And just like your breath turning into a faint mist on a cold morning, energy began to condense into matter. Quarks clung together to form protons and neutrons. Electrons appeared. The universe became a hot, dense soup of subatomic particles, all steeped in radiation. In the first 3 minutes, just 3 minutes, the first atomic nuclei took shape. Protons and neutrons collided and stuck, forming deuterium, helium, and a trace of lithium. That was the only window when the universe was hot enough for nuclear fusion. After those 3 minutes, it cooled too much. The window closed. But atoms still didn't exist yet. Electrons were zipping around too fast and too hot to be captured by nuclei. The universe remained a plasma, an electrically charged fog that was opaque to light. Photons bounced endlessly off free electrons, constantly scattered, unable to travel far. It was like trying to peer through a thick, impenetrable mist. Then, around 380,000 years after the Big Bang, something miraculous happened. The universe had cooled enough, down to about 3,000 degrees, for electrons to finally slow down and be captured by nuclei. The first atoms formed. Mostly hydrogen. Some helium. Simple, but stable. And in that moment, the universe became transparent. Light could finally move freely through space, no longer scattered at every turn. For the first time, the universe could be seen. That light, the light from that moment, stretched and chilled over billions of years, is what Penzias and Wilson discovered. It's the glow modern telescopes map in astonishing detail, giving us a portrait of the universe in its infancy. But even after light escaped, the universe remained dark. No stars. No galaxies. Just a vast, almost uniform cloud of hydrogen and helium gas, spreading across space, cooling, drifting quietly in the dark. Astronomers call this era the cosmic dark ages. It lasted for hundreds of millions of years, a long pause between the glow of the Big Bang and the first starlight. A breath. A waiting. The universe resting in darkness until something new could be born. But it wasn't completely still. Remember those tiny ripples, those slight fluctuations in energy from the earliest moments? They were still there. And gravity began to work on them. Slightly denser regions pulled in more matter. Slightly emptier regions became even more empty. Slowly, over millions of years, the gas began to clump, gathering into denser pockets. And eventually, around 100 to 200 million years after the Big Bang, those pockets grew dense enough, hot enough, for something extraordinary to happen. A star ignited. Then another. And another. All across the universe, in the darkness, light began to shimmer again. The first generation of stars, huge, blisteringly hot, brilliant, flared into existence, burning through their primordial hydrogen and piercing the dark. It was one of the most beautiful moments in cosmic history. The cosmic dawn. The end of darkness. The birth of light. Pause here for a moment. Let that image settle. Picture it, a vast, silent, black universe, and then, slowly, like fireflies appearing at dusk, tiny lights begin to glow. A few at first. Then thousands. Millions. Billions. Until the universe glowed once more, not with the afterglow of the Big Bang, but with the light of stars. And those stars weren't just beautiful. They were furnaces. In their cores, the pressure and heat were so intense that atomic nuclei fused together. Hydrogen fused into helium. Helium into carbon. Carbon into oxygen. Oxygen into neon, magnesium, silicon, iron. Every heavier element, everything the Big Bang couldn't make, was forged inside stars. And when those massive first stars ran out of fuel, they exploded in brilliant supernovae, scattering those elements across space. Carbon. Nitrogen. Oxygen. Iron. All the building blocks of planets. Of life. Of you and me. We are made of starlight. Literally. Every atom in your body, except hydrogen, was forged in the core of a star or in its explosive death. The calcium in your bones. The iron in your blood. The oxygen in your breath. All of it born in stars billions of years ago, billions of light years away. You don't just live in the universe. You're part of it. You're made of the same stuff as the stars. You are the universe experiencing itself, thinking about itself, marveling at itself. It's one of the most beautiful ideas in all of science. We aren't separate from the cosmos. We are the cosmos. We are how the universe knows itself. And all of that unbelievable, impossible wonder, began with a single moment. A moment when space-time itself sprang into existence. A moment when everything we know burst out of an impossibly small point and began the long, slow, beautiful journey from chaos to complexity, from simplicity to life. But that still leaves the biggest unanswered question. The one every child asks, the one every philosopher wrestles with, the one that keeps scientists awake at night. What came before the Big Bang? If the universe had a beginning, what came before it? What caused it? What existed when there was no space-time at all? These aren't easy questions. And the truth is, we don't know the answer. But we do have ideas. Hypotheses. Strange and beautiful possibilities. One possibility is that the question itself doesn't make sense. Remember, time began with the Big Bang. There was no before the Big Bang because there was no time. Asking what happened before time existed is like asking what lies north of the North Pole. There's no answer, not because we don't know it, but because the question doesn't apply. But some physicists aren't satisfied with that. They suggest that maybe the Big Bang wasn't the absolute beginning, but just one chapter in a far older, larger cosmic story. Maybe the universe cycles, expanding, then contracting, then bouncing back in another Big Bang. Each cycle lasting billions of years, and we're living in just one of them. Or maybe our Big Bang was just one of countless others, each one creating its own universe, with its own physical laws and its own history. A multiverse, where creation happens over and over, each universe like a bubble in a vast sea of possibility. Or maybe, and this is the strangest idea of all, maybe the universe created itself. Quantum physics allows fluctuations, things popping into existence temporarily thanks to the uncertainty woven into reality. Maybe the entire universe is a quantum fluctuation. One that didn't disappear. These are deep ideas. Strange ideas. And they're mostly speculative. We don't have evidence for them, yet. But they remind us that the universe is stranger than we imagine. And maybe stranger than we can imagine. The universe had a beginning. 13.8 billion years ago, everything burst from a point and has been expanding, cooling, and evolving ever since into all the complexity we see around us. Stars. Galaxies. Planets. Life. Consciousness. You, lying here in the dark, thinking about all of it. The miracle isn't that we understand everything. It's that we understand anything at all. That we, tiny creatures on a small world, can look up at the sky and decode the history of the cosmos. That we can measure light from the moment of creation. That we can trace our origins back to the first seconds of time. In the journey ahead, we'll return to something closer, more intimate. We'll explore the present moment, that now we always inhabit. We'll ask what it is, how long it lasts, and whether everyone experiences the same now. But for now, rest. Let your breath slow. Let your eyes close, if they haven't already. Because you are part of this story, the ancient, beautiful story of the universe discovering itself. And that story continues, even as you sleep. Right now. Only now. This moment, as you lie here, reading these words, feeling the weight of the blanket, hearing the distant sounds of the night. This is the only moment you've ever truly experienced. Not yesterday, that's just memory. Not tomorrow, that's only imagination. There is only now, always now. But what is now? It sounds like such a simple question, almost too simple. Yet the moment you start thinking about it, it becomes one of the deepest mysteries of existence. How long does the present, that now, actually last? A second, a millisecond, an indivisible instant. And the moment you try to catch it, it's already gone, slipping into the past, replaced by a brand new now. An ancient Greek philosopher named Heraclitus once said that you can't step into the same river twice. The river is always flowing, always changing. By the time you step into it again, it's different water, a different current. And maybe, he suggested, you're different too. Every moment is new. Every now is unique. But if every moment is different, why do we feel like the same person from one moment to the next? Where does the sense of continuity come from? How can there be a you that stretches through time if time is just a chain of separate nows, each one disappearing the instant it arrives? This is where science meets philosophy, where physics touches consciousness. And what we discover is stranger than we expect. Let's start with how your brain creates your sense of now. Because as it turns out, your now isn't a single point in time. It's a window, a span of about 2 to 3 seconds. Psychologists call this the specious present. It's the slice of time your brain uses to blend events together into one unified experience. When someone speaks to you, you don't hear each word as a separate event, you hear the whole sentence as one unit. When you listen to a melody, you don't hear scattered individual notes, you hear a flowing line, the notes linked together in time. Your brain is doing something extraordinary. It takes events that happen at different times, one a fraction of a second ago, one right now, one a fraction of a second later, and weaves them into a seamless experience. It creates a stretched out now, a present with room to breathe, a moment with space for things to unfold. But here's where it gets weird, different parts of your brain operate at different speeds. Information from your eyes reaches your brain faster than information from your ears. Signals from your fingertips arrive sooner than signals from your toes. So when you touch something and look at it at the same time, those signals don't actually reach your brain at the same moment. They're slightly out of sync. But you don't notice any of that. You feel like everything is happening simultaneously. Because your brain waits, gathers all the signals, lines them up, syncs them, and presents you with a single, polished experience of now. In other words, your now isn't real time. It's edited, processed, orchestrated. It's something your brain constructs, a convenient way to organize experience, not a fundamental feature of the universe. And then there's consciousness, the greatest mystery of all. Why do you have an experience of now? Why is there something it feels like to be you, in this very moment? Why does the present feel so vivid, so immediate, so present? We don't know. It's one of the biggest unsolved questions in science. Neuroscientists can show you which regions of the brain fire when you're aware of something. They can track electrical signals and measure chemical activity. But no one can explain why all that neural machinery produces a subjective experience, the feeling of living through a moment. Philosophers call this the hard problem of consciousness. How does matter, neurons firing, molecules moving, give rise to experience? How does physics become feeling? How does a brain become a mind? And when it comes to time, things get even stranger. If physics tells us that all moments exist at once, that past, present, and future are all equally real within spacetime, then why does consciousness experience them in sequence? Why do we feel a now sliding through time instead of perceiving our entire life all at once? Some physicists propose that consciousness itself ties into the arrow of time. Remember entropy, the rise of disorder? Maybe consciousness requires entropy. Maybe the sensation of time flowing, the sense of now moving from past to future, is a built-in consequence of how complex systems like the brain process information in a universe where entropy is always increasing. In other words, you experience time because your brain creates memories. And creating memories requires entropy. So the arrow of time, the direction from past to future, becomes woven into the structure of consciousness. It's a beautiful idea. But it still doesn't fully explain why now feels the way it does. Why this moment, the one you're living in right now, feels special. Why it feels real while the past feels like memory and the future feels like possibility. Some philosophers argue that this specialness is an illusion. They say there is no objective now, only a series of brain states, each containing a built-in sense of nowness, but no single moment is actually privileged over any other. The feeling that this now is real while all other nows are memories or potentials is a trick of consciousness. But even if that's true, even if now is an illusion, it's a beautiful one. It's how we experience being alive. It's how we feel connected to the world, to each other, to ourselves. Take a breath. Feel this now. Don't analyze it. Just experience it, the touch of the blanket, the darkness of the room, the sound of your breathing, the thoughts drifting across your mind. All of it is happening in now. Now your brain is stitching together from sensory signals, memories, expectations, and about 2 seconds of real processing time. And here's the truly astonishing part, your now isn't the same as anyone else's. Not just because different brains process time differently, but because, as Einstein showed us, there is no universal now spread across the cosmos. Time is relative. It moves at different rates depending on how fast you're traveling and how much gravity you feel. Which means your now, the set of events you consider to be happening at this moment, isn't the same as someone else's now, especially if they're far away or moving relative to you. Imagine 2 astronauts drifting through space, separated by billions of kilometers. One is moving toward you. The other is moving away. From the perspective of the one coming closer, a certain set of events on Earth is happening now. From the perspective of the one drifting away, a different set of events, maybe hours or even days apart, is happening now. Both are correct. Both nows are equally valid. There is no single moment that the entire universe agrees on as now. Each observer has their own now, shaped by their position and motion through spacetime. It's almost overwhelming, isn't it? Not only is now hard to define and even harder to pin down, it isn't even the same for everyone. Each of us lives inside our own personal universe of now, subtly different from everyone else's. But here's the astonishing part, in spite of all that physical and neurological complexity, now still feels simple to us. It feels direct, clear, undeniable. Right this moment, you're not thinking about entropy, or relativity, or neural signals. You're just here. Present. Experiencing this moment as if it's the only real thing. And maybe that's exactly how we're meant to think about it. No matter what physics says, no matter what philosophy argues about, now is all we ever truly have. It's the only place life actually happens. The past is gone, we can't change it. The future hasn't arrived, we can't be sure of it. Only this, now, this moment, is available to live. Eastern philosophers figured this out thousands of years ago. Buddhism teaches living in the present moment, not getting tangled in regret or pulled into anxiety, but fully inhabiting whatever is happening right now. Meditation, across many traditions, is really the practice of paying attention to the now, to the breath, the sensations, the stream of consciousness flowing through this instant. Modern science has started uncovering why this matters. Studies show that people are happier when they're present, when their minds aren't drifting to the past or the future but are anchored to what's happening right here. When we lose ourselves in a moment, reading a book, playing music, talking with a friend, or simply sitting quietly, we tap into a deep kind of happiness psychologists call flow. In those moments, time seems to disappear. Not because it stops, but because we stop tracking it. We dissolve into the experience, and the gap between me and now shrinks until they feel like one. That's one of life's beautiful paradoxes. The best way to experience time is to forget it. When you're watching the clock, counting the minutes, waiting for something to end or begin, time drags. It feels heavy, slow, dull. But when you give yourself fully to something, when you let yourself be swept into the now, time slips by unnoticed. Hours feel like minutes. Days feel like hours. And as you lie here, on the edge between waking and sleep, maybe you're feeling that right now. Time gets hazy. The past and future fall away. Only this, now, remains, each breath, each thought, each sensation, gently melting into the next. This is a different kind of time. Not time measured by clocks, but time that's lived, felt, experienced from the inside. Subjective time. Psychological time. The kind that only makes sense from the perspective of consciousness itself. And maybe that's the most important kind of time. Because we don't live in the universe of atomic clocks and Einstein's equations. We live in a universe of experience, where time slows when we're afraid, speeds up when we're joyful, and seems to stop when we love. There's an old poem by the Persian poet Rumi. He wrote, "Past and future veil God from our sight, burn both of them with fire." What he meant was this: by living fully in the now, unbound by what has passed or what hasn't arrived, we touch something deeper. A kind of reality beneath time, beyond time. Not every scientist would agree. Some would say time is all there is, that there's no timeless reality underneath it. But even they'd admit there's something special about the present moment. It's the only place decisions happen. The only place actions unfold. The only place life is actually lived. The past is written. It's fixed in memory and record. The future isn't written yet, or if it is, we haven't read it. But the now. This now is where the story is being told. It's where you're writing your own story, one moment at a time, one breath at a time, one choice at a time. Pause here. Feel the weight of that. You're living inside the one moment you have access to. This moment. This now. And it vanishes the instant you grasp it, replaced by another now, and another, in an endless stream. But maybe that isn't a tragedy. Maybe it's a gift. Because every new now is a new chance. A chance to notice. A chance to feel. A chance to choose how you want to show up in your own life. In these quiet seconds, as you lie in the dark, you have the chance to experience a distraction-free now. No phone to check. No to-do list to worry about. Nowhere to be, no one to perform for. Just this now, stretching out in a soft, peaceful stillness, inviting you to rest within it. And as you do, as you let yourself sink deeper into this now, time might start to feel different. Not fast or slow, but timeless. As if you're no longer moving through time, but floating inside it, like a leaf resting on a calm lake. It's a beautiful place to be, the boundary between wakefulness and sleep, where consciousness drifts, where time loosens its grip, where the now expands into something gentle and unbounded. Soon, we'll explore one of the most fascinating questions about time, whether we can travel through it. Whether we could visit the future, or return to the past. What physics says, and what imagination dreams. But not yet. We'll get there when we're ready. For now, stay here. In this now. In this moment. Where everything is quiet, and time, in all its mystery, becomes nothing more than a soft backdrop to the stillness of the night. Imagine stepping into a machine, a strange little device woven from light and mathematics, and popping out tomorrow. Or next year. Or 1,000 years from now. You could witness events that haven't happened yet, meet people who haven't been born, watch inventions that don't exist come to life. Or maybe you'd rather go the other way, back into the past. Walk through ancient cities, witness history unfold, talk to people long gone. Maybe, just maybe, change something that shaped the world. Time travel. Few ideas have gripped the human imagination more tightly. From ancient myths to modern movies, we've dreamed of slipping out of the time stream, drifting through the past and future the way we stroll through space. But is it actually possible? Do the laws of physics allow such a thing? Or is it just a beautiful, impossible dream forever out of reach? As it turns out, the answer is more complicated than you might expect, because time travel isn't just possible, it's already happening. We're doing it right now. Just not the way science fiction stories like to picture it. Let's start with traveling to the future, because that one's easier. Remember Einstein's discovery from the last chapter, that time slows down when you move fast. The faster you go, the slower your time flows compared to everyone else's. This isn't an illusion. It isn't a trick. It's simply how the universe works. So if you want to visit the future, all you need to do is move very, very fast. Hop onto a spaceship, accelerate to near the speed of light, fly around for a while, then return home. When you do, you'll find that far less time has passed for you than for the people on Earth. You might have aged a few years, while Earth has aged decades, even centuries, depending on how fast you were traveling. That's time travel. Real time travel. And it doesn't break a single law of physics. In fact, we've already done it, at least on a tiny scale. Astronauts aboard the International Space Station, orbiting Earth at about 28,000 kilometers per hour, are drifting slightly into the future every day. Only a fraction of a second, about 0.007 seconds after a year in orbit, but it's measurable. They age just a little bit more slowly than we do down here. Of course, to get a bigger effect, you'd need much higher speeds. With today's technology, that's impossible. But in theory, nothing stands in the way. All you need is a fast enough spaceship. There's another route to the future: gravity. Time also slows down near massive objects. So if you could get close to something with incredibly strong gravity, say, a black hole, and hover near it, your time would crawl compared to the rest of the universe. An hour for you could be years for everyone far away. When you finally left, you'd emerge in their distant future. And once again, this is real physics, not sci-fi. The movie Interstellar got this part right. The characters land on a planet near a black hole where an hour equals 7 years elsewhere. That's gravitational time dilation, and it's entirely allowed by the laws of nature. So traveling to the future? Completely possible. Difficult, sure. Dependent on technology we don't yet have, absolutely. But nothing about it breaks the universe's rules. But traveling into the past? That's where things get a lot stranger. Most physicists think that going backward in time, if it's possible at all, would create unsolvable paradoxes. And the most famous one is the so-called grandfather paradox. Imagine you build a time machine and jump back to a moment before your father was born, and, by accident, you prevent your grandparents from meeting. That would mean your father is never born. Which means you are never born. But if you never existed, how could you go back in time to stop them from meeting in the first place? It's a logical loop with no escape, a contradiction that breaks reality. So maybe nature simply forbids time travel to the past. Maybe the universe has some rule, a law we haven't fully uncovered yet, that doesn't allow causality to be violated. The past is fixed. You can't rewrite it. And because of that, you can't return to it. But not all physicists give up so easily. Some have proposed clever workarounds. One idea is called the principle of self-consistency. It says that if time travel to the past is possible, only those trips that don't create paradoxes can ever happen. In other words, if you go back in time, everything you do was already part of history. You can't change the past because you were already in it, you always were. It's a strange idea. It means that if you try to go back and alter something, you'll fail. Not because someone stops you, but because the universe refuses to allow contradictory loops. Reality bends itself to keep the timeline consistent. Another idea, an even weirder one, is the multiverse hypothesis. It suggests that if you go back and change something, you're not actually changing your past. Instead, you're creating a new timeline, a parallel universe where events unfold differently. In your original timeline, history stays the same. But in the new one, everything has diverged. So you could go back and stop your grandparents from meeting, but you'd only be stopping them in another universe, not the one you came from. You still exist because you originated in the untouched timeline. No paradox, just countless branching timelines, each a little different from the last. Sounds like science fiction, right? And it is, or at least, we have no evidence for any of it. But these are the ways theoretical physicists try to reconcile backward time travel with the laws of physics. And here's the really strange part, Einstein's equations actually do allow time travel to the past, under certain very specific conditions. One possibility is something called a wormhole. Picture spacetime as a sheet of paper. Normally, to get from one point to another, you travel across the surface. But what if you could fold the paper so the 2 points touch? Then you could punch a hole through and step across, a shortcut through spacetime. That's a wormhole, a tunnel connecting 2 distant points in the universe. And according to some theories, if you manipulate one properly, you could link not just 2 locations, but 2 different times. One end might sit in 2025, the other in 1925. Step through, and you've gone a century into the past. There's just one problem. We've never seen a wormhole. We don't know if they exist naturally. And even if they do, they might be wildly unstable, collapsing the moment anything tries to pass through. To keep one open, you'd need a form of exotic matter with negative energy, something we've never observed and maybe doesn't exist at all. So wormholes remain theoretical, mathematical possibilities, not engineering projects. Another idea involves rotating space. A physicist named Kurt Gödel, famous for his work in mathematics, showed that if the universe were rotating, it could contain closed time-like curves. These are paths through spacetime that loop back on themselves. Follow one far enough, and you return to the moment you started. But once again, there's a catch: our universe doesn't seem to be rotating. So while Gödel's solution proves that time travel to the past isn't forbidden by general relativity, it doesn't mean it can happen in the universe we actually live in. Maybe the answer isn't hiding in classical physics at all, but in the strange, shimmering world of quantum mechanics. At the quantum level, the rules shift. Particles can exist in several places at once. They can slip through barriers they're not supposed to cross. And, strangest of all, they sometimes seem to know things about the future in ways that feel impossible. There are experiments where measuring a particle now appears to influence what happened to it in the past. Physicists call this delayed causality, or delayed choice. It's not time travel in the traditional sense, but it does hint that the relationship between past, present, and future at the quantum scale is far more tangled than we imagined. Some physicists even suggest that information, if not matter, might be able to move backward in time under certain quantum conditions. But even that idea is controversial and barely understood. The truth is, we don't know whether traveling into the past is actually possible. Our equations allow for it in a few extremely special scenarios. But every time we find a theoretical path to the past, we also find enormous barriers, energies we can't reach, forms of matter we don't know how to create, or cosmic setups that don't match the universe we live in. And maybe that's the point. Maybe nature has a built-in bias against traveling to the past. Some physicists call this the chronology protection conjecture, the idea that the laws of physics, in some way we don't yet understand, prevent paradoxes by making backward time travel impossible. Or maybe it is possible, just incredibly rare, requiring conditions so bizarre they never actually occur in practice. But pause for a moment and consider this: if traveling to the past were possible, why haven't we met any time travelers? It's a classic question. If humans, or any civilization, eventually develop time travel technology, someone would surely come back to our era. Curiosity alone would bring them here. They'd want to study history, witness great events, understand how it all began. So where are they? There are a few possible answers. One is that time travel simply isn't possible and never will be. Another is that it works, but you can only travel back to the moment the first time machine was built, meaning no one from the future can visit us until we create one. A third possibility is that they are here, just hidden, observing from afar, careful not to disturb the timeline. Or the strangest idea of all, maybe the future doesn't exist yet to send anyone back. Maybe we live in a universe where the future is truly open, unwritten, and therefore, no future travelers can come from a place that hasn't formed. These are deep mysteries that blur the line between physics and philosophy. Do we have free will? Is the future already set? Is time something we can manipulate, or is it a fundamental part of reality that we're forever bound to? Take a breath. Let these ideas settle like golden dust in a quiet room. Time travel, its concept, its possibility, its mystery, captivates us because it touches something deeply human. We all carry regrets. Moments we wish we could redo. People we wish we could see again. Experiences we long to relive. And we all hold hopes and fears for the future. Things we want to know, outcomes we desperately want to see, questions waiting for answers. Time travel promises freedom from the helplessness of the present, the feeling of being trapped in this one moment, unable to visit others. It offers the dream of roaming the past and future the way we wander through space. But maybe, just maybe, the impossibility of time travel is its own kind of gift. If we could change the past, it wouldn't be solid anymore. Memories would lose meaning. History would turn liquid. Our sense of identity, of who we are and where we come from, would dissolve into uncertainty. And if we could see the future, it wouldn't be open. Every choice would feel hollow. Every decision predetermined. The mystery of life, the thrill of not knowing what comes next, would disappear. So maybe we are exactly where we're meant to be. Bound to the present, moving forward at 1 second per second, unable to go back, unable to peek ahead. Living in uncertainty, making choices without knowing where they lead, carrying the past as memory but never touching it again. There's a kind of beauty in that. A kind of breath. A sense that each moment matters because it happens only once and never again. And as we dream about time travel, as we imagine what it would be like to leap across centuries or revisit lost days, we are already traveling through time every single day. Not with machines or equations, but simply by existing, by living. Every breath pushes you deeper into the future. Every thought leaves a trace in the past. You are a time traveler, moving through the four-dimensional fabric of spacetime, carving your own path, leaving your own story behind. And that story, your story, is written by the choices you make in moments like this. In quiet. In darkness. On the edge between today and tomorrow. Time travel remains a mystery. Maybe possible, maybe impossible. Maybe only forward, maybe both ways. Maybe waiting for us in some distant era, or maybe forever out of reach. But what we do know is this: you're moving through time right now. And the path you take, not through space, but through choices, meaning, and the way you live each moment, is the most important journey of all. Later tonight, we'll go farther than ever before. We'll travel to the end of time itself and ask, can time end, and if so, what does that look like? But for now, rest. Let your imagination settle. Let sleep come, if it wants to. Because in dreams, we travel through a different kind of time, where past and future blend, where moments leap and overlap, where everything happens inside a strange, eternal present. And when you wake up, you'll have traveled into tomorrow. No machines needed. Just time doing what it always does, carrying us forward, one moment at a time, into a future that hasn't been written yet. Imagine being able to see farther than anything humanity has ever explored, not just billions of years ahead, but trillions. Quadrillions. Distances so vast the numbers stop meaning anything, a future so remote the universe itself becomes almost unrecognizable. What would you find there? Not the bright stars we see tonight, not the swirling galaxies alive with color and motion. Instead, you'd find a universe that has aged, cooled, and slipped into a kind of silence that's hard to picture. Stars fade one by one as their fuel runs out. Galaxies drift apart, pushed by the steady expansion of space. And eventually, in a cold darkness deeper than anything we've ever known, even time itself may start to lose its meaning. This isn't bleak sci-fi. These are the predictions drawn straight from the laws of physics. And tonight, as you drift towards sleep, we're going to explore what awaits the universe in the unimaginably distant future, and whether time itself might one day come to an end. Not with fear, but with wonder. With curiosity. Because even in the farthest predictions of a cosmic ending, there's a strange kind of beauty, a reminder of the vast scale of existence, and of how precious each moment is precisely because it doesn't last. Let's start with what we know. The universe is expanding. Galaxies are moving apart. And more than that, the expansion is speeding up. There's a mysterious force physicists call dark energy, making up about 70% of everything, pushing the cosmos outward faster and faster. We don't know what dark energy is. We only know it's there, and it's accelerating the expansion. And if that continues, if dark energy stays constant, the universe will keep stretching forever, growing larger, colder, and emptier as time rolls on. So what does the distant future look like? For the next few billion years, a brief moment on the cosmic clock, things will still look familiar. Stars will keep shining. Galaxies will keep spinning. Our sun has around 5 billion years left before it swells into a red giant, swallowing the inner planets, then collapsing into a white dwarf, a small, dim ember slowly cooling in the dark. But go farther. In 1 trillion years, 1 trillion, most stars will have burned through their fuel. The gas clouds that create new stars will be gone. A few last suns will flare and fade, leaving behind a universe filled with dark remnants, white dwarfs, neutron stars, black holes, and cold wandering rocks. Our galaxies, the Milky Way, Andromeda, and the others in our local group, will merge into one giant supergalaxy. But beyond our neighborhood, every other galaxy will have drifted out of sight, pushed so far away by the expansion of space that their light can never reach us again. If someone were to look up at the sky in that distant era, they would see nothing. Just their lone galaxy, suspended in endless darkness. In a million years, an interval so huge it slips right past our ability to grasp, even those last, lonely remnants will begin to change. Rogue planets will slowly drift into the black hole at the center of their galaxy. Dead stars will collide and merge. The cosmos will settle into a cold graveyard of dark objects, drifting quietly through an ever-widening void. But even black holes, the most seemingly eternal structures in the universe, don't last forever. In the 1970s, a physicist named Stephen Hawking discovered something astonishing: black holes evaporate. Very slowly, unimaginably slowly, but they do lose mass through a quantum process known as Hawking radiation. For a large black hole, the kind formed from a collapsing star, this takes a mind-bending amount of time. We're talking about 10 to the power of 67 years, a 1 followed by 67 zeros. Far longer than the universe has existed. Far longer than any span of time we even have words for. But eventually, even the giants, those supermassive black holes anchoring the centers of galaxies, weighing billions of suns, will evaporate in one final whisper of light. And after that? Physicists call the next stage the heat death, the ultimate ending of a universe that expands forever. It's a state where everything has been stretched too thin, where energy is perfectly dispersed, no temperature differences remain, no gradients, nothing left to drive processes or spark change of any kind. Entropy, the arrow of time, will have reached its maximum. The universe will settle into perfect equilibrium. And in that equilibrium, time, at least in the way we experience it, loses its meaning. Because remember, time moves forward only because entropy increases. The past feels different from the future because things are constantly drifting toward greater disorder. But if entropy is maxed out, if there's no disorder left to increase, there's no meaningful difference between before and after. No events. No changes to measure. Time won't exactly stop, but it will stop mattering. Nothing will happen. No memories will form. No processes will unfold. There will only be existence, timeless, unchanging, endless. It's a somber picture, isn't it? A universe empty and cold, stretching on forever in perfect stillness. No light. No warmth. No life. No thought. Just particles drifting through the dark, so far apart they'll never meet again. But take a breath. Let your mind rest there for a moment. Because here's the part that truly matters: all of this lies in a future so distant it makes every human timescale look microscopic. Far beyond anything that concerns us. Far beyond any future humanity could witness, any civilization could endure, any star could shine. Right now, in this moment, the universe is still young. Just 13.8 billion years old, a brief flicker compared to what lies ahead. We live in a privileged era, a time when stars still burn, galaxies still glow, and the cosmos is full of life and possibility. And maybe, just maybe, there is hope even for that far-flung future. Because there are other possibilities, other futures the universe might stumble into. One possibility is that what we know about dark energy just isn't the full story. If dark energy changes over time, if it grows stronger, the universe might not only keep expanding forever, it could accelerate in a wild, runaway way. Eventually that push would become so intense that it would tear space itself apart. Galaxies would be ripped open. Stars would be torn to shreds. Planets, molecules, even atoms would be pulled apart piece by piece. Physicists call this the Big Rip, a violent ending where the very fabric of spacetime is stretched past its limit and snaps. It wouldn't unfold slowly like heat death, it would be sudden, happening within a finite span of time, maybe tens of billions of years. But we don't think this is the most likely outcome. Dark energy, as far as we can tell, seems stable. So heat death is still the most widely predicted fate of our universe. Unless, there's another option. What if the universe doesn't expand forever? What if, at some distant point in the future, dark energy weakens or reverses? What if gravity eventually wins, and the universe begins to shrink? In that scenario, galaxies would stop drifting apart and start falling back together. Space itself would contract. And eventually, over trillions upon trillions of years, everything would collapse inward in a mirrored replay of the Big Bang. Physicists call this the Big Crunch, the Great Collapse. The universe folds in on itself, growing denser and hotter as it shrinks until everything fuses once again into a single point. A singularity. An ending that echoes the beginning. And after that? Maybe nothing. The end of time, just as there was a beginning. Or maybe, and this is the beautiful part, the Big Crunch could bounce. Maybe it could spark a new Big Bang, birthing a brand new universe with new laws of physics, new stars, new possibilities. A cosmic heartbeat, an endlessly cycling universe expanding and collapsing over and over again, each cycle lasting billions of years, each one a chapter in a story that never truly ends. It's a lovely idea. But current evidence doesn't support it. The universe appears to be expanding too fast to ever reverse. So unless there's something we don't yet understand about dark energy, and that's entirely possible, the Big Crunch doesn't seem to be in our future. But there is one last possibility. A strange, unsettling, fascinating one. What if the vacuum, the emptiness of space itself, isn't stable? Quantum theory suggests that there might be different states of vacuum, some with lower energy than others. And if our vacuum isn't the lowest state, if it's only metastable, then at some point, somewhere, it could drop to a lower state. That transition would start at a single point, a bubble of true vacuum, and expand outward at the speed of light. Inside the bubble, the laws of physics would be different. Matter as we know it might not exist. Atoms would fall apart. Everything would be wiped out. Physicists call this vacuum decay, or the Big Slurp. And the frightening part is that it could happen at any time. No warning. No prevention. One moment the universe behaves as usual, and the next, a silent wave of destruction sweeps across everything. But before that thought keeps you up tonight, remember this: if it ever happens, it would arrive at the speed of light. We would never see it coming. One moment everything is fine, and the next, there is no next. No pain. No fear. Just, the end. And realistically, the odds are incredibly tiny. If our vacuum were on the verge of decay, it likely would have happened already, sometime in the last 13.8 billion years. The fact that we're still here, that the universe still exists, that stars are still shining and you're lying here reading these words, suggests that our vacuum is probably stable enough to last for a very, very long time. So then what? How does the universe end? With a whimper or a bang? With ice or fire? With a slow fade into darkness, or a violent collapse into a single point? The truth is, we don't know. We can make informed guesses based on what we observe, and right now, heat death looks like the most likely outcome. But the universe has surprised us before. It has shown us things we never imagined: black holes, dark energy, accelerating expansion. And it may still be holding more surprises, waiting to be revealed. But now, let's come back here. Back to now. Back to this moment you're living in. Because that's the beautiful thing about all these stories of endings, they remind us how precious the present really is. They remind us that everything, even the universe itself, is temporary. Nothing lasts forever. Nothing stays the same. And maybe that's exactly what makes life beautiful. If the stars shone forever, their light wouldn't feel precious. If time had no direction, moments wouldn't matter. If nothing ever ended, nothing would ever truly hold meaning. But stars do burn out. Time does move forward. Moments slip by and never return. And that's why each moment matters. Every breath. Every thought. Every connection we make, every experience we live, every time we pause to marvel at the beauty of the world. We live in a finite universe, not necessarily in space, maybe that's endless, but in time. It had a beginning. It will have an end. And in between, in this brief and breathtaking interval, there's us. You, lying here in the dark, on a planet orbiting a middle-aged star in an ordinary galaxy, in a universe slowly expanding toward one of its many possible fates. But in this moment, none of that matters. What matters is this breath. This thought. This quiet. This connection to something larger than yourself, something vast and ancient and achingly beautiful. Time will someday end. But not today. Not tonight. Tonight, it's still flowing, still carrying us forward, still offering chances for wonder, for growth, for connection. And maybe that's time's final lesson, not about how it began or how it ends, but about how we choose to live within it. About how we choose to spend the precious moments we're given. The ancient philosophers understood this. They spoke of memento mori, remember that you will die. Not as something grim, but as something freeing. Because when you remember that time is limited, you stop wasting it. You stop postponing what matters. You start paying attention, loving more deeply, living more fully. The same is true for the universe. When we remember that the stars won't shine forever, that the universe itself runs on borrowed time, we look up at the night sky with deeper awe. We feel more grateful for this extraordinary era we were lucky enough to be born into, an era of light, of warmth, of possibility. We live in a young universe. A universe bursting with energy and potential. And even though the far future may be cold and dark, the present is vibrant and radiant and full of wonder. So take a slow breath. Feel the weight of the blanket, the softness of the pillow, the darkness of the room around you. Know that you are part of something vast, a story stretching from the Big Bang to an unimaginable future. A story that includes every star, every planet, every living thing that ever was. And in that story, you have your own role. Small, maybe, on a cosmic scale. But not small in meaning. Because you are one of the ways the universe becomes aware of itself. One of the ways it experiences beauty, and wonder, and love. And in this moment, this quiet, dark moment, you're doing something extraordinary. You're reflecting on time itself. You're thinking about the beginning of everything and the end of everything. You're holding the entire history of the universe in your mind, from the first seconds after the Big Bang to the final frozen ages. That's a kind of miracle. That matter, atoms forged in stars, arranged in intricate patterns inside your skull, can think about such things. Can wonder. Can marvel. Time is a mystery. It's the structure of reality and an illusion of consciousness. It's the endless river and the eternal now. It's what began with the Big Bang and what will end, somehow, someday, so far in the future we can hardly imagine it. But tonight, in this moment, time is something simpler. It's the distance between this breath and the next. It's the quiet space between this thought and the one that follows. It's the feeling of peace as you let yourself drift, let go, sink into sleep. And in sleep, time changes again. It becomes dream time, non-linear, tangled, beautiful. Past and future blur. Moments leap and overlap. You might soar through years in a heartbeat or live a lifetime in an instant. And then, when you wake, you'll return to linear time, the time of clocks, of calendars, of moments flowing from past to future. But maybe, just maybe, you'll see it a little differently. Maybe you'll remember that time isn't a prison, but a gift. Maybe you'll remember that each moment is precious precisely because it passes. Maybe you'll remember that you are part of something vast, a cosmic story still unfolding, still full of mystery and wonder. So rest now. Let your eyes close. Let your breath slow. Let your thoughts drift like leaves on a quiet stream. Time will still be here when you wake. Still flowing. Still mysterious. Still beautiful. And you'll still be part of it, moving through it, carving your own path through spacetime, writing your own story in the great book of the universe. One breath at a time. One moment at a time. One beautiful dream at a time. Good night. Let time carry you. And as it does, know that you're drifting through the greatest mystery of all, not how time begins or ends, but what it feels like to live inside it. This moment. Right now. Forever appearing, forever fading, forever beautiful.